Dear class, last time in the machine learning course we finished the discussion on multiple features and the issues related to those multiple features, and we started discussing another type of problem of machine learning, supervised machine learning, which is classification. So in the first chapter we have already discussed what is classification. So classification is to classify or to divide something uh, into classes. So we discussed in chapter number 1 some of the examples of classification are, for example, these are some examples that are occurring, that are used in everyday life. So examples are email. Every time we are using an email, we don't know, but basically there are some algorithms running in the background, some machine learning algorithms that divide the emails coming which are spam or not spam. So some of you maybe know that sometimes emails are sent to us which we don't want. For example, there is some lottery, or sometimes there are some advertisements coming which we don't like to receive. So, and if those emails are coming in huge numbers, then we will not be able to get our important messages out of a uh, big chunk or big pile of messages. So I don't know if you people know this or not. Almost 10 to 12 years ago or before that, spam messages were a very big problem for anyone dealing with the emails. So all the times when emails we open the emails, there were at least 20-30 spam emails coming which were not useful, which were waste of time. And out of those emails, for me, I had to search the important ones. But slowly, as the algorithms they improved, now we don't see these emails. For my account, for example, I don't receive any spam email, maybe one or two emails after a month or 2 months. So this is one of the very important practical application of machine learning, that it can automatically identify some emails that are not good, they are a waste of time. Another important use of machine learning for classification is very important, and it's practically used. It's the online transactions. So most of the people around us, they are using the ATM cards, the Visa cards. So these Visa cards, they can be used for shopping on the internet. So if someone gets to know the card and your name, all the details, then they can use your card on the internet for shopping. So in that case, it is important for the machine, for the computer, to know that someone is using your card in a bad manner as a fraud. So how it can know? It can know based on some important characteristics. For example, based on the past information, you always use your card online maybe, or not online. You use your card only in the evenings, not at a very late time in the night. For example, not after 12 at night. But if someone is trying to use your card from Australia, so maybe they are not using at the same times as you use over here in your country. So this one is not important, but there are some other parameters. One important parameter is you don't travel outside Oman. So in that case, the machine will be very sure if your card is being used by a person in Australia or Brazil, then it means that there is a very high chance that this is a fraud transaction. So this is basically one other area of machine learning where a lot of input parameters are given, and these algorithms are running all the time. Even now they are running all the time, and they are detecting if some transaction which is going to happen it can tag it as a fraud. If it is a fraud, then it is quickly passed on to a human person that can go on and check it in more details. And the third application we saw for classification problems, it was the tumor classification to find out that some patient he has a cancer which is malignant or benign. So malignant tumor means it's in very bad shape, and I told you that cancer treatment is expensive and not so easily available. So doctors, they try to put their efforts more on the cases that they think can be saved, the life can be saved. Even you can also put this classification in present day scenario. You all know that this is the time that we have this coronavirus. So based on the symptoms of the coronavirus, for example, for how long time a patient is sick, and what are the other symptoms, he has the temperature or not, he has coughing, he is feeling pain, all these things can be fed to a machine, and we can predict, and also some other factors like age and gender, and if a person has other habits like smoking or he has some other disease. So all these factors can be given to machine, and the machine can predict that this person has more chances of dying or surviving because of the coronavirus or not. So in that case, you know, sometimes the resources are very, very less. So for example, in the case of present day scenario, there are very less number of hospital staff and hospital equipment available. And when the patients are more, then in that case, doctors have to decide which patients they will give more priority. So that is the case when we need classifications. There are many more serious applications of classifications. Practically, if you ask me, out of these two types of supervised learning, and the regression and the classification, classification is more important and it's used a lot more in practical applications. So remember, when we discussed about the classification, we saw this earlier in chapter 1. Classification is normally done, we have two classes. For example, we call one of the class as negative class and the other one as a positive class. Negative you can represent normally, this is the normal trend, we represent one class by 0 and the other by 1. You have seen it in your practice exercises also. And remember, in the last part of the chapter, we will see that classification can be done when we have more than two classes. So in that case, we represent the classes by the numbers, for example, 0, 1, 2, 3, and it can keep on increasing. Clear? So we have discussed earlier this thing, if you remember, that we have got these red cross are the tumors. So you see the tumors and you see the result of the past data. So for example, these tumors over here below, they are the ones that were not malignant because they were not dangerous and the patients they survived in the past. Whereas some other tumors, and you see on the x-axis there is tumor size. So when the tumor size was increasing, there were some other patients which did not survive, their tumor size was bigger. So you can clearly see there is a relation. When the tumor size is increasing, then it is more difficult to save the patient. So based on this thing, you see that in the classification we want to make some sort of division between the two classes. We want to divide, there should be a cutoff point. So in this case there can be one cutoff point like this blue vertical line, or there can be some other cutoff points, it depends. For now we don't know. So practically this one looks, for now this vertical line looks more better, so I put a red line here. And this classification divides the two categories separately, making them, for example, dividing them. One side is the patients whose tumor is not serious, on the other side the patients whose tumor is serious. Now let's say if you, so this is it. Now in this case, remember, if you remember in the regression, the H, always we represent H, and we call the H as our hypothesis, and we say that this is the output of our model. So in regression, if you remember, was a continuous value. So H was equal to, if you remember, theta 0 plus theta 1 x. And if you remember, at that time we used the H as a simplified form. So theta 0 we remove it, and theta 1 x we used for a simplified model. Here in this case, in the classification, we are going to use the H as an output that can have a value that ranges between 0 and 1. Okay, so we try to keep the value of the H between 0 and 1. So if the value of H, it goes above 0.5, it is equal to 0.5 or above, we say that the output, it is 1. The class of this type of cancer, it's 1. Or if it is less than 0.5, then in that case we say that the output is, we predict that Y is 0. The output is 0. Okay, so this is it. In this case, now we get the H value, which is not a continuous very big range number. It's a number, it's still a floating number, but it has a very small range between 0 and 1. Clear? So here are the so here you see in the classification problem, the output should be between 0 or 1, and H can be a number. It is possible that H can be a number very big, much bigger than 1, or it can be a number much smaller than 0. It is also possible, but still, for practical reasons, we have the H between 0 and 1. Okay, this type of problem of classification, we call it logistic regression. The word logistic regression should not be misleading. This is a typical, very typical interview question. For job interviews, you can get a question that what is logistic regression, what type of regression it is. So remember, important thing, that logistic regression is not the regression problem. It is not supervised learning method of regression. Logistic regression is used for classification, whereas the other one was linear regression, that is used for regression. So the word used over here is misleading, but it's used for classification, not for regression. The output H is between 0 and 1, and we use it to predict the output. So what is it? We will see the little bit of details of the hypothesis, how it is represented. Okay. So we saw the hypothesis. So what is a hypothesis, how it works? So remember, this thing we discussed in the last lecture, so we will go through it again. So we have got over here the hypothesis. And hypothesis, if you remember, in the case of linear regression, it was represented by a simple formula. So if you remember over there, the formula was theta 0 plus theta 1 x. Here the hypothesis is represented by a little more complex formula, and the formula over here, it is called as sigmoid function. So this is the formula you see over here. This is sigmoid function. The function is called sigmoid. What it does is that this formula takes the same value. So we are making it simple, we keep it simple. Instead of theta 0 plus theta 1 x, we write over here only theta x. So you can say theta is your tunable parameter, and we give this theta x as an input to the sigmoid function. So theta x, it comes as a power to the e. So e, if you remember or not, it is basically a constant, and its value you can search on the internet. Its value is almost I think 2.71 something. So no need to worry about this, but just for now remember this is a constant e. So what happens in this formula? 1 over 1 plus e to the power minus z. So here you come, this one. So z is basically this thing which is represented by theta x. So z is basically your parameters, the theta which is tunable, which you want to find, and the x which is the input. So the output of this sigmoid function, so sigmoid function is used in logistic regression. So if you remember, in the case of linear regression, your output was a line. So it can be any slope straight line, a straight line, but its slope will be anything. Here you have got a sigmoid function, and its output is a line that is called that is almost in this shape. You can't say it's an S shape, but it is something. Sometimes people use the word that it's S shape, but I wouldn't prefer this thing. You can say that it's some sort of a slope. Okay, so on the negative side, the value, so after the minus 1, for example, so the value, it on the negative side, it touches almost 0, and on the positive side it touches 1, but it is never equal to 0. It is never equal to 100% equal to 0. So when the z value, so remember, on the x-axis you have the z, and on the y-axis you have the value of the h. Okay, so when the z value on the y-axis, you can say this is g of z. So g of z is basically used same as the h. Okay, so when the z value, it is negative, very large negative value, the output will be something very very close to 0, and it is not 100% 0. Even if the value of z is equal to infinite, then only the output will be 0. And z value, when it is positive, then the g of z will try to be very close to 1, but not perfectly 1. And what about the middle point? The middle point is somewhere when the z is equal to 0 point, and the g of z is equal to 0.5, and this 0.5 occurs when the z is 0. So when z is 0, in that case only your output is 0.5, and 0.5 almost also means that your h you predict output is 1. So when value becomes more than 0.5, you predict it as a class 1. If it is less than 0.5, you predict it as 0. That is the summary for logistic regression. That's what we want to do over here. Clear? Pause the video, think over it. Make sure all the things are clear to you people over here before we go next. One thing very important to remember is that the logistic regression is the second most important concept. Sometimes it's more important than the linear regression in our problems. So here you see, so sigmoid function is used for logistic regression, and sigmoid function is also called as logistic function sometimes. Clear? So what is sigmoid function? Sigmoid function is basically this representation, 1 over 1 plus e minus e to the power minus z. So this was it. And what you want to do is that you want to find out what should be the output y value. It should be 0 or 1. They have given over here some things related to probability estimation. I don't think that you should be going to that side. It is a little bit more difficult. So what we want to do, we will keep it simple for ourselves for now. So probability, this one, leave it. So so we discussed the decision boundaries. So here is again your logistic regression function. So you have got h equal to g of the theta x, and the g value is given to you. So when theta is greater than 0, what happens? Then in that case, when the theta is greater than theta x, sorry, theta not theta, theta x is greater than 0. In that case, the z value is greater than 0, and what you get is you get some value of h which is greater than 0.5. So practically, when your z is positive, the output is 1, and when the z is negative, the output is 0. So 0.5, less than 0.5 means the output class should be 0. So this is the summary. So when you want to predict y equal to 1, then in that case the h should be greater than greater than or equal to 0.5, and when h is less than 0.5, you predict that the output is 0. Is it clear? So here it is. You see over here a problem where you have got the two classes. So one of them you see circle and the other one you see cross, and you want to predict you want to find out the boundary, the decision boundary. So we call this line decision boundary. So if you remember, in the regression case, we want to have a line that was as closely possible it was representing the data lines in the case of housing prices. Here we want that the line should be there in between the two classes, and it should predict the two classes as perfectly as it is possible. Clear? So we call this decision boundary because it makes a decision between the two classes. Okay. Decision boundary can be a linear boundary, just like in the case of you saw previously in linear regression, or sometimes it can be polynomial boundary. For example, it can be a quadratic equation. So here you see one of the example of h function. You see g, and in the bracket you see this function. So it means that you always apply the sigmoid function on whatever input you have. That is the important difference between linear regression and classification. So remember, if you are using g is important because g will turn everything, every input value, which is maybe a very big value, maybe this is 5000, this will convert it into some value between 0 and 1. Is it clear? So remember, sigmoid output is always between 0 and 1. So G is must used for logistic regression. Inside the G, the function can be used, any function can be used. Maybe it's a linear. So here you see this function is linear. So this is the intercept theta 0. Here you have theta 1 x1, and the first input x1, and the second input theta 2 and x2. So it is still a linear function, but high dimensions. So we want to predict y equal to 1. In that case, here they have given one example solution where they want to solve it. So the decision boundary y equal to 1 will be there when you have got this equation over here. So they have predicted some example. So this is just an example. Don't consider it something that is very strict. Here it is given, the three values of theta are given. So for this equation, theta 0 is let's say -3. Okay. Theta 1 and theta 2 both are 1. Okay. So this is your equation now. Now for this equation, now this is your equation which is theta x. Now if you remember in the last slide I told you that if this value of theta x it is positive, then the output class will be 1. So if it is positive, that means this side should be greater than equal to 0. So when it is greater than equal to 0, in that case you can easily, if you remember your college mathematics or calculus, you can move this minus 3 on the other side. No restriction, it will minus 3 will become plus 3 on the other side. It is equal to x1 plus x2 greater than equal to 3. So this will give you one simple formula that can give you the output in terms of input values x1, x2. So x1 and x2, their sum when it is more than 3, and it means the output will be 1. Or on the other hand, when x1 or x2 is less than 3, in that case the output will be 0. Is it clear? Pause it, go through all these formulas, equations, make sure you understand all of them. Very important. Next thing, sometimes as in the case of linear regression, sometimes in the regression problems also, sometimes I told you we don't go through linear regression. There are other types of regression like polynomial regression. There are many other types of equations you can use. So here is also the same thing, that sometimes you cannot use the linear regression. For example, you see over here a typical example. Inside you have got one class and the outside you see a circle of another class. Now if I ask you, take a line and give me a classification, classify the two classes, separate them. So with any straight line you can never do it. Never possible. For example, if I try to do like this, no, not possible. So for any combination, you will always have many values left from one or both of the classes. So decision boundary, linear decision boundary is not usable in all the cases. So this is one example where linear decision boundary is not usable. So in that case, we use non-linear decision boundaries. So non-linear decision boundaries we will not be going in detail in this course, but they can be any formula. So for example, here you see one formula, x1 square plus x2 square equal to 1. There are so many different types of websites available that allow you to make a plot of the formulas. So there is one for website, I suggest you go over there. It's called Desmos. Search it on Google, Desmos. Go on Google, search it, Desmos, and over there try to write this formula and try to plot it. When you plot this formula, this plot for this formula is like this, the orange, not the purple circle you see over here. So it will give you this purple circle, and this purple circle gives you the decision boundary that is perfectly separating the two classes. Is it clear? So this is one example of nonlinear decision boundary. So when so if you have an equal to sign over here, that means that you are representing this circle perfectly. Whereas if you put an inequality greater than equal to 1, it means the class that is outside this circle, greater than equal to 1. Okay. And you can even use many other functions. For example, you can use this very complex function as a decision boundary. So it is theta 0 plus theta 1 x1 theta 2 x2. Then you use quadratic parameters, theta 3 x1 square, theta 4 x2 square. Now these square terms, they will make it a very complex function. It will not be a straight line. So let's suppose this line over here, this function you see over here, it is represented by this thing. Okay. So in that case, what happens is that the function, it is encircling one class. So for example, y equal to 1 class is inside the function, and outside the function there is another class. This is what happens practically. Okay. So whenever, for example, for this case, x1 square plus x2 square, you predict y equal to 1 if this thing over here, this formula is greater than equal to 0. So from this you try to derive the same thing, and if it is less than equal to 0, then it gives you something inside the circle class. So you see over here, outside, inside the circle y equal to 0, outside the circle it is y equal to 1. Same is the case for the other parameter, you see. So maybe the function over here, it is using this formula. So these are just examples. It can have any formula, we don't know. Okay. So go through it, pause it, and think over it, and ask questions in the group. This is a very small class of 3 or 4 students, so ask as many questions as you people want. I would really appreciate it.